The title of this course is Kinematics of Machines. So let us start our discussion with the definition of these two words, namely machines and kinematics. Broadly speaking, we can define machine as a device for transferring and transforming motion and force or power from the input, that is the source, to the output, that is the load. Let me repeat. Machine is a device for transferring and transforming motion and force from source to the load. The motion needs to be transformed as it is being transferred from the source to the load. The type of transformation that is needed is decided by the nature of the input motion that is available and the type of output motion that is desired. Some typical examples of the available input motion and desired output motions we are listing now. Maybe the input motion available is in the form of continuous rotation, whereas the desired output motion is a rectilinear motion, or the vice versa. The input motion is a rectilinear motion and we need the output motion in the form of continuous rotation. Sometimes the input motion may be continuous rotation, whereas the desired output motion is in the form of to and fro oscillation, or again the vice versa, that is the available input motion may be to and fro oscillation along a straight line, however the desired output motion may be continuous rotation. Sometimes both input and output motion may be continuous rotation, but they may have to take place at different speed. Sometimes the input motion may be continuous rotation, however the output motion desired is that of an angular oscillation. Sometimes we also need from continuous input rotation to be transformed into intermittent rotary motion. At this stage, let us talk of a real life machine, that is the most common machine tool, which we call a lathe. Here the input motion is available at the shaft of the driving motor, which is the input motor, normally located at bottom left end of the machine. This motion has to be transferred to two different locations, that is to the headstock to provide motion to the job and also to the tool post, that is to provide motion to the cutting tool. Let us see during these two transfer processes what kind of transformation is taking place. As we know, the job has to rotate continuously, so headstock has to be rotated, but has to be rotated at a different speed than from the input motor, depending on the size of the job. Whereas the tool post has to move along a straight line starting from the same input motion. Thus, we need two different kinds of devices to transfer and transform the motion from the input to the output. As a second example, let us look at the model of this tipper damper. Here, the input motion is linear, provided by a hydraulic actuator, and this linear motion has to be transformed into a rotary motion of this dumping bin. Thus, the linear motion at the hydraulic actuator from the input side is transferred to the bin and is also transformed into the rotary motion. One more point one needs to watch in this machine is that during the dumping position, the damper is locked and cannot be disturbed by any accidental disturbance. Normally, in most such machines, various components undergo very little deformation. Consequently, these components can be assumed to be rigid. Within the paradigm of rigid body, the relative motion between various components can be studied from the viewpoint of geometric constraints without any reference to force. And the subject matter which deals with this geometric constraint of relative motion without any reference to the cause of the motion, that is the force, is called kinematics. We repeat, the subject which deals with only geometric aspects of motion without any consideration of force is known as kinematics. For the study of kinematics, a machine may be referred to as a mechanism, which is a combination of interconnected rigid bodies capable of relative motion. During the study of kinematics, that is of a mechanism, the idea of motion or relative motion predominates and the idea of force takes a back seat. As an example of a mechanism, let us look at this one, which is a windshield wiper mechanism for bigger vehicles like a bus. Here, the continuous rotation of the drive motor is converted into to and fro oscillation of the wiper blade. Of course, the power available at the motor shaft is used to overcome the friction force between the blade and the windscreen. However, designer is primarily interested to ensure a proper range of oscillation of the wiper blade to generate the desired field of wiping. Consequently, we do not call it a wiper machine, but we call it a wiper mechanism. As a second example, let us look at this common pair of pliers. Here, if we want to study the relative movement between the two jaws, we can hold the lower jaw fixed and move only the upper jaw. As we see, these two jaws are simply hinged and the axis of the hinge is passing through this point. Consequently, all the points of this upper jaw are moving in circular arcs centered at this hinge axis. Consequently, it will not provide a very good grip on a flat object, and especially so if the object is long. However, we can design a parallel jaw pliers by using a suitable mechanism. Using this mechanism, as we see, the upper jaw is moving parallel to the lower jaw, and consequently it will provide a very good grip on a flat object. So, in such mechanisms, the generation of the specific motion characteristics is of primary interest rather than the forces or torque involved. A clue to the behavior of a mechanism lies in the interconnection. And these interconnections are technically called a kinematic pair. For the understanding of kinematics, a thorough understanding of the interconnections of the kinematic pair is essential. That is why we shall now discuss in detail various kinematic pairs and the kind of relative motion that are permitted at these interconnections, which are kinematic pairs. Before we go into the discussion of different types of kinematic pair, let me define certain technical terms. The number of coordinates that are needed to describe the relative movement permitted in a kinematic pair is called the degree of freedom. As we said, in every kinematic pair there is some relative movement, and to describe that relative movement we need some coordinates. And the number of such independent coordinates necessary to completely specify the relative movement is called the degree of freedom. And the coordinates that are used to describe this relative movement is called pair variable. At this stage, let us recall that a free, that is an unconnected rigid body, which does not have any kinematic pair with some other rigid body, a completely free unconnected rigid body has 6 degrees of freedom in a 3-dimensional space. 3 of these degrees of freedom are translational, say along three mutually perpendicular directions x, y, z. So, there are three translations, one along x axis, other along y axis and other along z axis. The rest three are rotational. As soon as this free rigid body is connected to another rigid body through a kinematic pair, one or more of these 6 degrees of freedom are curtailed and only few are retained. Kinematic pairs can be normally classified under 3 headings, namely lower pair, higher pair and wrapping pair. In a lower kinematic pair, the two bodies which are connected by this pair has area contact. That means, suppose we talk of two bodies, namely 1 and 2, if they are connected by a lower pair, then at this connection body 1 will have a surface contact with body 2. Similarly, in a higher pair, the contact between the two bodies has only a line contact or a point contact. Whereas in a wrapping pair, one body completely wraps over the other. The typical examples is of a belt and a pulley, or a chain and a sprocket, where the belt completely wraps around the pulley or the chain completely wraps around the sprocket. There is another way of classifying the kinematic pair, namely sometimes it is called a form closed pair, sometimes it is called a force closed pair. Let me now explain what do we mean by form closed. If the contact between the two bodies at the kinematic pair is maintained by their geometric form, then we call it a form pair. Whereas if the contact needs to be maintained by the application of an external force, then we will call it a force closed pair. All these concepts will become clear when we get into specific examples. Next, we shall discuss all these various kinds of lower pair, higher pair through their schematic representation. I want to insist that the diagrams that will be shown is only for the schematic representation. Their physical construction can be very different, as will be exemplified when we get into specific kinematic pair. Let us now discuss 6 different types of lower pair. As shown in this slide, two bodies, namely body 1 and body 2, are connected by this kinematic pair, which is known as a revolute pair. This is a simple hinge joint. This portion of body 1 is a cylindrical pin which goes into a cylindrical hole in body 2. Also note these two collars on body 1. To study the possible relative movements between these two bodies 1 and 2, let us consider body 1 to be fixed, and let us see what type of motion you can give to this body number 2. Obviously, the body cannot translate along this vertical direction. The body 2 cannot translate in this horizontal direction, and the body 2 also cannot translate perpendicular to these two directions. Consequently, all the 3 translational degrees of freedom of body 2 has been restrained by this revolute pair. The only relative motion that is permitted is rotation of body 2 about this vertical axis. The pair variable theta represents this relative rotation between body 1 and body 2 about this vertical axis. We should also note that this particular revolute pair is characterized by this axis, which is a fixed line in space. The next slide will show what is known as a prismatic pair. In this prismatic pair, again if we hold this body 1 fixed, then body 2 can only move along this vertical direction. No other rotation of body 2, no other translation of body 2 is just not possible. Consequently, this S representing the relative sliding between body 1 and 2 is the pair variable, and this has single degree of freedom just like a revolute pair. However, I would like to emphasize one very critical difference between a revolute pair and a prismatic pair. If we go back to the revolute pair, we saw that this is characterized by this axis, which is a line fixed in space, whereas in this prismatic pair the translation is along vertical direction, and that can be represented by all vertical lines. We do not need any fixed line in space. So, this is only a direction, not an axis. At this stage, I would like to emphasize that these two diagrams are only schematic. For example, a revolute pair can be constructed by a bearing between the shaft and the foundation. So, the physical construction of a revolute pair can be very different, because that bearing also allows a rotation about a fixed axis. Similarly, a piston within a cylinder in an IC engine, for example, forms a prismatic pair, because the only motion possible between the piston and only relative motion between the piston and the cylinder is possible along the length of the cylinder. The next slide shows what is known as a screw pair. In the screw pair, the body 1 is a screw and the body 2 is a nut. So, if we fix body 1, then the only relative motion of body 2 that is possible is rotation theta about the axis of the screw, but as the nut rotates, it also translates along the axis of the screw. So, S also can represent the relative motion. It may appear that it has 2 degrees of freedom because 2 pair variables, namely theta and S, are required. But a little thought would convince us that this screw pair also has a single degree of freedom, because as rotation theta goes to 2 pi, if I say it is the rotation, so I represent it by change in theta. If delta theta goes to 2 pi, then change in S, delta S goes to L, where L is the lead of the screw. Thus, theta and S are not independent, but they are related by this expression, delta theta by 2 pi is equal to delta S by L. Consequently, only one of these, either theta or S, is needed to completely specify the relative movement. The next figure shows what is known as a cylindric pair. Here there is a cylinder which is the body 1 passes through a cylindrical hole in body 2. So, if we hold body 1 fixed, then body 2 can rotate about this vertical axis, and we can also translate body 2 with respect to body 1 along this vertical direction. But here we see the pair variable theta and S are independent. I can keep theta equal to 0 and give any amount of S, or I can hold S equal to 0 and give any amount of theta. Thus, 2 pair variables theta and S are independent. Consequently, this cylindric pair has 2 degrees of freedom. The next slide shows what is known as a ball and socket joint. There is a spherical ball in body 2 and there is a spherical cavity in socket 1. This pair is known as a spheric pair. It is obvious from the schematic representation, if we hold body 1 fixed, then body 2 loses all its translatory degrees of freedom. It cannot translate in x, y or z direction. However, it retains all its 3 rotational degrees of freedom. These three rotational degrees of freedom can be represented by three independent angles, namely alpha and beta. These two angles, alpha and beta, locates the line OA in this three-dimensional space x, y, z, and these alpha and beta are completely independent. I can give any amount of alpha and any amount of beta and take OA somewhere else in this three-dimensional space. But even after locating this axis OA, there is another degree of freedom, theta, which denotes the spin of body 2 about its own axis OA. Thus, we have 3 degrees of freedom in this spheric pair, and the 3 pair variables are alpha, beta and gamma. Again, it is needless to say that this is only a schematic representation. Nobody would be able to make such a ball and socket joint. The obvious question is, how did the ball enter into the socket? The next kinematic pair, as shown in this slide, is called a planar pair. Here, as we see, body 2 can have translation along x direction given by the pair variable s, along the y direction given by the pair variable sy, and also rotate about the z axis given by the pair variable theta. And this sx, sy and theta are 3 independent coordinates. Consequently, planar pair has 3 degrees of freedom. The next figure shows a what we call a spheric pair, but you also note that this is force closed. Here, the spherical surfaces of body 1 and body 2 are maintained in contact in these 2 zones by the application of the spring force. We should also note that this is how in real life a spheric pair will be constructed, where this body 2 is assembled rather than making in one piece as shown earlier. Let us now recapitulate all these 6 types of lower pairs. As we said, a lower pair should have surface contact, and we must have noted that in all these schematic representation, the bodies 1 and 2 had contact over a finite surface. The first we discussed what we called a revolute pair. The symbol that is used for revolute pair is R, that is the first letter of this word revolute. This revolute pair is nothing what we in non-technical language call a hinge joint. The degree of freedom of this revolute pair is 1, and the pair variable is theta, which denotes the rotation. Next, we discussed what we called a prismatic pair, which is nothing but a sliding joint. The symbol for prismatic pair is P, which is again the first letter of the word prismatic. Here also the degree of freedom was 1 and the pair variable was S. Then we discussed a screw pair. The symbol for screw pair is H. To remember this H, it will be nice to remember that screw is in the form of a helix, and it is the first letter H of helix we are using to represent the symbol of a screw pair. The degree of freedom in screw pair was also 1, and the pair variable could be either theta or S, which were related by this relation delta theta by 2 pi is equal to delta S by L. Then we discussed what we called a cylindric pair. The symbol is C. Here the degree of freedom is 2, because we need 2 independent variables theta and S to represent the relative rotation and relative translation. Then we discussed spheric pair. The symbol for spheric pair we are using G. To remember this G, maybe we can remember the spheric pair we can also call a globular pair, and G is the first letter which is used to represent the symbol of a spheric pair. Here the degree of freedom is 3, and the pair variables as shown in that sketch were alpha, beta and theta. Lastly, we had what we called a planar pair. We cannot use the symbol P, which has already been used for the prismatic pair, so we give it a new symbol called E. In German language, plane is called Ebene, starting with the letter E, and we are using that letter E to represent a planar pair. The degree of freedom in a planar pair is also 3, and the 3 pair variables were Sx, Sy, representing translation in 2 mutually orthogonal directions, and theta z, that was the rotation about the perpendicular axis, which was represented as z axis. Now that we have discussed all kinds of lower pairs, let us get into what is known as a higher pair. In a higher pair, as told earlier, the contact between the two bodies takes place only along a line or at a point. As we see between the pair of gear teeth or between a cam and follower mechanism. The next slide schematically shows a higher pair between body 1 and body 2. As we see, if we restrict the relative motion of body 2 with respect to body 1 in one plane, then there can be only relative translation in this direction and rotation about this axis. And this is the line contact between body 1 and body 2. So, this is a higher pair. This diagram again shows a higher pair between body 1 and body 2. As the body 2 moves relative to body 1, and assuming that the motion is restricted in this xy plane, then to describe this relative motion completely, we need two coordinates, namely Sx and theta z. Sx representing the relative sliding and theta z representing the rotation about the z axis are completely independent. Thus, if a higher pair is used in a planar mechanism, then a higher pair will have 2 degrees of freedom and 2 pair variables, namely Sx and theta z. Now that we have defined all types of kinematic pairs, let us talk about the classification of different types of mechanism. Broadly speaking, we can classify mechanism under 3 headings, namely planar, spherical and spatial. In a planar mechanism, all the points of the mechanism move in parallel planes, and all these parallel planes can be represented by a single plane, which is called the plane of motion, and a single view perpendicular to this plane of motion reveals the true motion of all the points of a mechanism. As an example, let us look at this planar mechanism. This is called a 4R planar linkages. Here we have 4 rigid bodies, namely 1, 2, 3 and 4, which are connected by 4 revolute pairs at O2, A, B and O4. As this linkage moves, the input motion is transferred to the output motion through this rigid body 3. The input shaft at O2 and the output shaft at O4 are parallel. Not only that, what we can see that all the 4 revolute joints have parallel axes A, O2, O4 and B. There are 4 revolute joints, but the axis of all these 4 revolute joints are parallel and perpendicular to the plane of motion. The next figure shows what is known as a 4R spherical linkage. Here again we have 4 rigid bodies connected by 4 revolute pairs, one here, one there, one here and one there. But the axis of all these 4 revolute pairs intersect at one point, namely here. This linkage can be used to transmit input motion from shaft 1 to output link number 4. The input is link 2, link 1 is fixed. There is a revolute pair. If I rotate this input shaft, the motion is transmitted through all these revolute joints and ultimately the output link 4 rotates. So, this is a mechanism to connect 2 shafts whose axes are not parallel but intersecting. Such a joint is known as a Hooke's joint. This figure shows again a mechanism with 4 revolute joints, but here we call it a 4R spatial linkage because the points of all these links move neither in parallel planes nor on the surfaces of spheres. They move in a 3-dimensional space. And as can be clearly seen that the axes of these revolute pairs are skewed in space in the sense they are neither intersecting nor parallel. This linkage has a name, it is called a Bennett's linkage. It should be mentioned that unlike in a 4R planar linkage or in a 4R spherical linkage, in this 4R spatial linkage there can be relative motion only for some specific dimensions. Now that we have discussed different kinds of kinematic pair and different types of linkage, let me say what is the subject that we study in kinematics. In kinematics there are 2 types of problems. One is called analysis. In kinematic analysis, one is given a mechanism and the task is to determine the various relative motions that can take place in that mechanism. The other problem is what is known as kinematic synthesis. In a synthesis, one has to come up with a design of a mechanism to generate prescribed required relative motion characteristics. This course will be addressing to both of these problems, namely kinematic analysis and kinematic synthesis.